Today we'll start the chapter oscillation. So, oscillation is an interesting phenomenon of physics. In our daily life, we see the number of examples of oscillatory motion. For example, motion of needle of sewing machine, the motion of prongs of the vibrating tuning fork, the oscillations of a spring, the vibrations of musical instrument like that of guitar or violin. Okay, so we know that there are the number of examples for the oscillatory motion. So all in these cases, the motion repeated after a certain interval of time is a periodic motion. Here, the motion of an object is mostly to and fro or up and down. So let us see about the explanation for the oscillatory motion. So we'll consider about the oscillatory motion. So oscillatory motion, it is a periodic motion, and in this chapter we shall see that the displacement, velocity and acceleration, it is represented by sine and cosine functions, and these functions are known as harmonic functions. Therefore, an oscillatory motion obeying such function is known as harmonic functions, or these functions are known as harmonic functions. Okay, so let us see about the part for the oscillatory motion. So we know that we'll consider about the motion. So know that motion is the change in position of object with respect to surrounding, that is called as the motion. The motions are mostly divided in the form of three types. The first, that is linear motion or translation motion. So know that linear or translation motion means in which the object or body moving along a straight line path. The second, that is the rotational motion. So know that rotational motion means in which the body performs the uniform circular motion and it is rotated about an axis passing through its center. And the third, that is the oscillatory or vibratory motion. So in this chapter we will discuss about the part for oscillatory or vibratory motion. So know that the oscillatory motion, it is a periodic motion. Okay, so the next point, that is the explanation of periodic motion. So what is the periodic motion? So know that periodic motion means any motion which repeats itself after a definite interval of time, and that motion is called as the periodic motion. And this periodic motion, it is taken the form of two types. The first, that is the rotational periodic motion, and the second, that is the oscillatory periodic motion or vibrational periodic motion. Okay, so the rotational periodic motion means the rotational motion of a body which repeats itself in equal interval of time with constant angular velocity is called as rotational periodic motion. Means, for example, motion of tips of hands of a clock, the motion of blades of rotating fan, like that. Okay, and while we consider about the vibrational periodic motion, so vibrational periodic motion means in which the particle repeats its to and fro motion along the same path in equal interval of time. Okay, and that motion is called as the vibrational periodic motion. For example, oscillation of a simple pendulum, vibrations of atoms in molecule, the motion of needle of sewing machine, like that. Yes, we will discuss about that example. Okay, so we'll consider about this topic. We'll take the next point, that is the periodic time. Periodic time means a body performing periodic motion goes on repeating the same set of movement, and the time taken for one such set of movement is called period or periodic time. Okay, and while we can say about the vibratory motion, so it is a motion in which the particle repeatedly moves to and fro along the same path, and that is called as the oscillatory or vibratory motion. And during that oscillatory or vibratory motion, if the path is a straight line, then the motion is called linear simple harmonic motion, and if the path is an arc of circle, then it is called as angular harmonic motion. Okay, means during oscillation, if the path is straight line, so that is the linear simple harmonic motion. And if the path it is an arc of circle, then that is called as angular simple harmonic motion. Okay. While see about the next, that is the note to be right. Every oscillatory motion, it is a periodic motion, but every periodic motion need not to be an oscillatory motion. Then the next point, that is the expansion for linear simple harmonic motion. So know that linear simple harmonic motion means it is a harmonic motion or simple harmonic motion in which the body or the particle oscillate or vibrate along a straight line path. Okay, during oscillation, so that is called as the linear simple harmonic motion. Let us see the figure, that is 5.1 ABC, that is spring mass oscillator. Then while we see about in this figure, place a rectangular block on a smooth frictionless horizontal surface, attach one end of a spring to a rigid wall and the other end to the block as shown in figure. Then while consider about this figure, A, pull the block having the mass EGM towards the right and release it. The block will begin its to and fro motion on either side of its equilibrium position. This motion is a linear simple harmonic motion. Well, in this figure B, that is the equilibrium position in which the spring exerts no force on the block. If the block is displaced towards the right from the equilibrium position, the force exerted by the spring on the block is directed towards the left as shown in figure A. Means due to the elastic properties, the spring tends to regain the block to its original shape and size, and therefore it exerts a restoring force on the block. This force, this restoring force, is proportional to the displacement. Means if the displacement is large, then the restoring force acting on the block is also large, and if the displacement is small, then the restoring force acting on the block is also small. While the direction of that restoring force is opposite to that of the displacement. Okay, means suppose x is the displacement, F is the restoring force. So this force F is directly proportional to displacement. Okay, and while neglecting the project sign, then we can write F is equal to minus kx, where k is the force constant and x is the displacement from the mean position. Okay, let us see in that figure. So F is equal to minus kx. Okay, then while if the block is displaced towards left from its equilibrium position, the force exerted by the spring on the block is directed towards the right, and its magnitude is proportional to the displacement from the mean position that is shown in figure C. Okay, so in that case we again found that the F is equal to minus K, means the restoring force is again directly proportional to displacement. They are in opposite direction. Now if the block is released from the right position, then the restoring force exerted by the spring, it can accelerate it towards its mean position. And while we say about the, according to Newton's second law of motion, the force is equal to mass into acceleration. So acceleration is equal to F by m. So substitute the F, so we'll get A is equal to minus K by m into x. Means in that case we again found that the acceleration is directly proportional to displacement. They are in opposite direction. Why? Because K, that is the force constant, and the m, that is the mass of block, is also constant. Means K by m is constant, then we say that the acceleration is directly proportional to displacement. They are in opposite direction. Okay, so when, as shown in figure A, when the block is moving towards the left, means it can be reaches to its mean or equilibrium position. So at that time the value for displacement, force and acceleration to be decreases, and its velocity to be increases. And when the block is reaches to its mean position or equilibrium position, so at that time we found that the velocity of block is maximum. So when its velocity is maximum, so the kinetic energy of the block is also maximum. So due to of that reason, it is not comes to at rest position, means at mean position, it is not comes to rest, but it is continuously moving towards left. Okay, and when it can be continuously moving towards left, so its velocity again decreases, and when its velocity is again 0, so it comes to rest at that position. It means at this position the velocity is minimum, but the displacement is again maximum, because that is the maximum displacement from the mean position. Okay, so in that case the spring get to be compressed. So due to the elastic property, the spring again regain to its original shape and size, so it can again exert the restoring force on the block, and the block is again moving towards its mean or equilibrium position. So the process goes on repeating that causes the block to oscillate on either side of its equilibrium position, means its mean position. So such oscillatory motion along a straight line path is called as linear simple harmonic motion. Okay, so let us see about the definition for the linear SHM. So linear SHM means, the linear SHM is defined as the linear periodic motion of body in which force is always directed towards the mean position, and its magnitude is proportional to the displacement from the mean position. Okay, means in that case we say that in which force or acceleration is always directed towards the mean position, and its magnitude is proportional to the displacement from the mean position. Okay, so that is the explanation for the part of linear simple harmonic motion. Okay, then next point, that is the differential equation of linear SHM. Okay, so let us see about the differential equation of linear SHM. So see about the notation. M, that is the mass, x is the displacement, F is the restoring force, K, that is the force constant, A is the acceleration, V is the velocity, and omega, that is the angular frequency. Okay, so you know that when we discuss about the part for linear SHM, so you know that in linear SHM the force is directly proportional to displacement. They are in opposite direction. So we can derive the equation F is equal to minus kx, where k is the force constant and x is the displacement from the mean position. So according to the Newton's second law of motion. So know that force is equal to mass into acceleration. Okay, so ma is equal to minus kx. Okay, and while we say about the velocity, so know that the velocity of particle is dx upon dt, and while we say about its acceleration, so acceleration is equal to dv by dt, so that is d square x by dt. Okay, so substitute that value in this equation, so we'll get m into what is the acceleration a, so that is d square x by dt square is equal to minus kx, so d square x by dt square plus k by m into x equal to 0. Okay, so that is the called as the differential equation of linear SHM. But let us substitute k by m, that is the constant. That constant is replaced by suppose omega square, where omega that is the angular frequency, and after substituting omega square, so we will get d square x by dt square plus omega square is equal to 0. Okay, and that is called as the differential equation of linear SHM. Okay, then let us discuss about the next point, that is the acceleration, velocity and displacement of SHM. Okay, so that is the total mathematical part. Okay, let us see about the expression for first acceleration, then we can determine the expression for velocity, then find out the expression for displacement of SHM. Okay, so we obtain at first the expression for acceleration. Okay, so we know that the differential equation of linear SHM. So what is the differential equation of linear SHM? So know that the equation is d square x by dt square plus omega square is equal to 0. So d square x by dt square equal to minus omega square x. But know that that is the formula for acceleration. Means acceleration equal to dv by dt and v means dx by dt. So acceleration is equal to d square x by dt square, that is the acceleration of particle performing SHM. So let us substitute that acceleration in that equation. So acceleration is equal to minus omega square x, and this is the expression for acceleration in terms of displacement x. Then next, so let us substitute acceleration equal to d square x by dt square. So the next step is d square x by dt square equal to omega square x. So d by dt into dx by dt is equal to minus omega square x. Then that is velocity, dx by dt is velocity, so dv by dt is equal to minus omega square x. So rearrange this term, means it is multiplied divided by dx, so dv by dx into dx by dt is equal to minus omega square x, but dx by dt means again velocity. Okay, so v into dv by dx equal to minus omega square x, so v dv is equal to minus omega square x dx. So after that taking integration on both the sides, so after integration, that is the integration of v dv is equal to minus omega square, that is the constant taken out from integration, so minus omega square integration of x dx. So after, so that integration, so integration of v dv is v square by 2 is equal to minus omega square, the integration of x dx is x square by 2 plus c. What is the c? So c, it is the constant of integration. Then next, then let us assume that when the particle is at extreme position, so that while the particle is at extreme position, so the velocity is considered to be 0. Okay, and what is the displacement? So know that the displacement is maximum. Okay, so let us substitute x equal to plus minus a. So what is the capital A? That is the amplitude. Okay, means let us substitute x equal to plus minus a, v is equal to 0. So substituting that value, so 0 is equal to minus omega square a square by 2 plus c. So c is equal to omega square a square by 2. Let us again substitute that value c in the before that equation. So after substituting v square by 2 equal to minus omega square x square by 2 plus omega square a square by 2. So take out common 1 half, and 1 half yet cancel. So the remaining is v square equal to omega square taken out common, so in bracket that is a square minus a square, or v is equal to plus minus omega under root of a square minus a square. Okay, and that is the equation for velocity of particle performing SHM. Okay, then after that find out the expression for displacement. Okay, so find out the expression for displacement. So let us substitute v is equal to dx by dt in that equation. So dx by dt is equal to omega under root of a square minus a square. So rearrange that term. So dx upon root a square minus a square is equal to omega into dt. Again taking integration on both sides. So integration of dx upon root a square minus a square is equal to omega dt. Okay, so this is the formula for sine inverse x upon a. Okay, is equal to omega, integration of dt is t plus phi. Okay, so what is in this term phi? So phi, that is called as the constant of integration. Okay, so sine inverse take on this side, so x upon a equal to sine omega t plus phi. So we'll get the last term is x equal to a sine omega t plus phi. Okay, and this is the expression for the displacement of particle at any instant. Then suppose while during oscillation, so know that the particle is moving from its mean to extreme position. Okay, so we can take the case first. Suppose the particle is at mean position, or particle starts from mean position. So when the particle starts from mean position, so what is the displacement? S equal to 0 and t is equal to 0. Okay, so when we can substitute that value. Okay, so after substituting we'll get x equal to plus minus a sine omega t. Okay, that is the equation for displacement when the particle starts from mean position. Okay, and while in the case second, when the particle starts from extreme position, so during that time what is the displacement x? That is plus minus a, the time is equal to 0. Okay, so after substituting that value, so in that case we'll get x equal to plus minus a cos omega t, or x equal to a cos omega t. Okay, means in that case this is the general expression for displacement. But if the particle starts from mean position, so what is the formula for displacement? That is x equal to a sin omega t. When the particle starts from extreme position, so what is the formula for displacement? That is x equal to a cos omega t. Okay, so that is the topic for explanation for equation of acceleration, velocity and displacement. Okay, then next point. Okay, so let us see about again the expression for displacement, velocity and acceleration at time t. Okay, so that what is the general formula for displacement? So know that its formula is x equal to a sin omega t plus phi. Then find out velocity. So what is the velocity? That is rate of change of displacement with time. So what is its differentiation? So that is a omega cos omega t plus phi. Then find out the acceleration. So what is the acceleration? That is rate of change of velocity with time. Okay, so we'll get acceleration is equal to a omega square sine omega t plus phi. Okay, so that is the acceleration, velocity and displacement at time interval t. Then let's see the next, that is the extreme values for acceleration a, velocity v and the displacement. Okay, so let us see about at first displacement. Okay, so know that what is the general expression for displacement? The general expression for displacement is x equal to a sin omega t plus phi. Well, consider at mean position. So at mean position, this term omega t plus phi is equal to 0 or phi. Okay, so well we can substitute, that is the sine 0 is equal to 0 or sine pi is equal to 0. So we get the displacement is minimum, and what is the minimum displacement? That is 0. Okay, means thus at mean position the displacement of particle performing SHM is minimum, that means 0. And while the particle is at extreme position, so at extreme position, what is the term for omega t plus phi? So its term is pi by 2 or 3 pi by 2. Okay, so when we substitute that pi by 2 or 3 pi by 2, so its value is 1. Okay, so we'll get x equal to plus minus a, and that is the maximum displacement. Okay, means when the particle is at extreme position, the displacement of particle performing SHM is maximum. Okay, then the next, that is the velocity. So what is the general formula for velocity? So that is general formula for velocity is v is equal to omega plus minus omega under root of a square minus a square. Okay, so at mean position, so that what is the displacement? So x equal to 0. So x equal to 0. So what is the velocity? Is formula is plus minus a omega. That is the maximum velocity, because we know that in linear SHM, when we discuss about the part for expression for linear SHM, so in that case we found that when the displacement is minimum, so velocity is maximum, and when the velocity is maximum, when the displacement maximum, so velocity is minimum. So we know it. So in that case, displacement minimum at mean position, so velocity maximum. And what is the formula for Vmax? So its formula is plus minus a omega. Means in that case the SHM is maximum. Okay, while consider about at extreme position, so know that at extreme position the x equal to plus minus a, and that is the maximum amplitude. Okay, so while we substitute x equal to a, so the value is 0. So what is the velocity? So velocity is 0, means the velocity is minimum. So SHM is minimum. Okay, means while we consider about display minimum, velocity is maximum, what is the formula for Vmax? That is a omega. When the display maximum, so velocity is minimum. Then see about the next term, that is the acceleration. So know that what is the formula for acceleration? So know that in magnitude its formula is acceleration is equal to omega square x. Okay, and while we can see about at mean position, so x equal to 0, so the acceleration is minimum. So what is its value? Minimum is equal to 0. And when the particle is at extreme position, so equal to plus minus a, so that the acceleration also maximum. So what is the formula for Emax? So its formula is plus minus omega square e, because we know that acceleration is directly proportional to displacement. When displacement is minimum, so acceleration is minimum. When displacement maximum, the acceleration also maximum. Okay, so that is the explanation for the extreme values for displacement, velocity and acceleration. Okay, then let us see about the next topic, that is amplitude, period and frequency of SHM. Then we'll see about the in this figure. So in that figure, MN, that is the straight line path, okay, and O, that is the mean position. Okay, so let us consider the particle P, and this particle P perform the linear SHM along a straight line path MN about the mean position O. Okay, then the displacement of particle. So what is the formula for displacement? So know that is equal to capital A sine omega t plus phi. The particle will have its maximum displacement, so that at maximum displacement, so sine omega t plus phi is equal to plus minus 1. So what is the displacement? So displacement is equal to plus minus a, and this is the amplitude of SHM. Okay, so what is the amplitude of SHM means? What is the definition? The maximum displacement of particle performing SHM from its mean position is called the amplitude of SHM. Clear that? Okay, then the next, that is the explanation for period of SHM. So what is the period? So know that it is the time taken by a particle performing SHM to complete one oscillation is called as the period of SHM. Okay, let us see about the equation for period of SHM. So we know that the displacement of particle at time t. So what is the formula for displacement? X equal to a sin omega t plus phi. Let us, we can take the time, that is after time t we can write t is equal to 2 pi by omega. Then let us find out the displacement. What is the displacement? So x equal to a sin omega and substitute t is equal to t plus 2 pi by omega plus phi. Okay, and after solving we get x equal to a sin omega t plus 2 pi plus phi. Okay, and what is the sin 2 pi? That is 0, so we'll get x equal to a sin omega t plus phi. Okay, means in that case we found that, or this can show that the particle is at same position after a time 2 pi by omega. Okay, means if we can take the time 2 pi by omega, and after that time the particle is returned to its original position. Okay, means in that case we assume that the particle completes one oscillation in time 2 pi by omega. Okay, so it can show that the small t. Okay, so it, sorry, it can show that the small t is equal to capital T, and that is t is equal to 2 pi by omega, and it is the minimum time after which it can repeats. Then while you consider about t is equal to 2 pi over omega. Okay, so in that case suppose we can take omega square. So omega square equal to k by m. So what is the k? That is force per unit displacement divided by mass, and we can write that is again force divided by mass, that is the acceleration. So we can write omega square equal to acceleration per unit displacement. Okay, so we can write capital T is equal to 2 pi by omega. So that is omega is equal to under root of acceleration per unit displacement. Okay, and while we can substitute that value in the form of omega square k by m. Okay, so we'll get t is equal to 2 pi under root of m by k. Okay, so that is the one of the formula for period in terms of mass m and force constant k. Then next let us see about the frequency of SHM. So what is the frequency? So the frequency means the number of oscillations performed by a particle performing SHM per unit time is called frequency of SHM. Okay, means in 1 unit time how many number of oscillations performed by particle, that is called as the frequency of SHM. Okay, so due to that reason the number of oscillations performed by a particle performing SHM per unit time, that is called as the frequency of SHM. Okay, and while we can say about in one oscillation, so what is the time? So that is t. So in unit time, so we can take 1 upon t, and what is the 1 upon t? That is called as the frequency of SHM. Okay, so we can write the formula for frequency is n is equal to 1 upon t. So now that t is equal to 2 pi upon omega, so we'll get the another formula is omega upon 2 pi, and while we substitute t is equal to 2 pi under root of m by k, so we get n is equal to 1 upon 2 pi under root of k by m. Okay, so these are the different formulas we can write for the frequency of SHM. Okay, so that is the expansion for amplitude, period and frequency of SHM. Okay, and after that the next topic, that is the reference circle method, that is the next actually our topic. And after that the next topic, that is the graphical representation of SHM. Okay, so both topics are omitted from our syllabus, so we can't discuss about that topic. In the next lecture we'll discuss about directly the next part, our next topic, that is the composition of two SHM, they can having for same period and along the same path. Okay, so that is the completion for the first part of our physics lecture. So thank you for watching this lecture.